The way that's named is completely different. Okay, looking at the first. So, first two categories, biggest thing is classify. So if I give you a compound, you need to be able to classify it. Does it fall in ionic or molecular? So let's just classify it. If I go to my handout, we're not going to start naming yet. We're going to just classify it first. So I'm going to skip around because I haven't introduced polyatomic ions. Okay. This is a purple handout I gave to you last week. If you don't have it, it's here. Yeah, I can always tell. Okay, looking at number 2, what two elements are involved?
Sulfur and fluorine.
Yeah, sulfur and fluorine. What are they? Metals or non-metals? They're non-metals. So both are non-metals. That would fall under molecular. Remember another name for this is covalent. Okay, so we're just identifying right now. Number 3, what would that fall under? Molecular or ionic? Ionic. Potassium is a metal, oxygen is a non-metal. I'm not looking at the numbers or anything like that. I'm just looking at, okay, is this a metal or a non-metal? What about number 4? Metal is your gold, iodine is your non-metal. So, you have a metal, non-metal, that is classified as ionic. What about number 5?
Molecular or covalent?
Yep. This is going to be molecular. Covalent because iodine is a non-metal, oxygen is a non-metal. So you're just looking at the periodic table, classifying them, and then figuring out what two categories they fall under. What about number 7?
Ionic.
Yeah, ionic. You have sodium, which is your metal, fluorine, which is your non-metal. So it's just classifying them. Okay, we'll get back to the other ones once I introduce that. So you just classify. Okay. When we're looking at the ionic category, one thing again you have to keep in mind. A metal likes to lose electrons. Non-metal likes to gain. So you have this perfect relationship, right? One thing wants to lose that electron, the other thing will gain that electron. And it's not like, don't think the metal is getting deprived or anything, right? Like, don't think it's like oh, you're just giving everything to the non-metal. The metal wants to lose that electron. It wants to do that. The non-metal wants to gain that electron. So it's not a bad relationship in that sense. Don't feel sorry for the metal.
It's not a toxic relationship.
Yeah. So when we look at this, it's kind of like, how would you say? Like, I like to cook, but some people may not think that's fun to do, right? They might see it as a chore. But I like to do that. So it's not, you don't need to feel sorry for me, right? I want to do that. I want to provide a meal, for someone, kind of thing. So it's not a bad thing. Now, for a different person, it might be different. But when we're looking at metals, one guy likes to lose, one guy likes to gain that electron. So when you see that, you have a positive and a negative. Because of that, when they come together, the partnership has to be neutral. Your charges always, always, always have to cancel out. So if you have something like this, here, calcium with the 2+, that's telling me it likes to lose how many electrons? Yeah, loss of 2 electrons. Now, the counterpart is the chloride ion, which is coming from chlorine. Now, if you look at this, notice I wrote it twice, because here it's losing 2 electrons. The thing is, chlorine only wants to gain 1. So because of that, you need to have 2 of them in order to accommodate these 2 electrons. So here you have 2 chlorines for every 1 calcium. So when you write this formula, it looks like this. You have 1 calcium for every 2 chlorine. And you do a subscript like this to show that. So if you look at this, notice the charges cancel out. You have a 2+ here, a 2- here. When you add them up, so when you look at the charges, they cancel out. And that's very, very important when you're showing the compound. Never, ever, ever, ever show the charges when you write the formula. Never do this. Never do that. That's like a dagger to my heart. Never do this. Here you're trying to show the charges, but the thing is, you have it written as a compound, which is neutral. So never show it like that. That's the appropriate way to write it. No charges. When you're showing the ions, you show them separate. So notice I don't have them together. That's the calcium ion. This is the chloride ion. So they're separated. When they come together, they don't have the charges any longer. Because the electrons were transferred. Calcium lost those 2 electrons, and then the chlorine gained 1 here, gained 1 here. So that charge is no longer there. You always have to remember that. What I said right here is just written out here when you're doing this. Now, you'll practice this and you'll start seeing the pattern. One of the things that you have to keep in mind, you always want it in the lowest possible terms. Meaning, if I do this, now I'm showing 2 calcium ions, right? So I need to have, here, I have a +4 and a -4. So the charges cancel out, but the thing is, if you look at this, this is not going to be in the lowest terms. Because if I write the formula, I have 2 calcium ions for every 4 chlorine ions. So if I look at this, notice what I can do to the 2 and the 4. What can I do? I can reduce it. So this becomes calcium chloride, just like that.
When we're reducing, are we just like dividing?
Yeah, you always want it in the lowest possible terms. Can you divide it to the lowest possible terms? Now, it just depends on the situation. It may be a situation where you can't do that, right? So are you able to divide both numbers by a particular number? Here I can divide both of them by 2 and get something like that. Now, let's say I have something like this. I have aluminum likes to be a +3, wants to lose 3 electrons. Now, I have oxygen in the mix. It likes to gain 2. Now, I have to figure out how many I need for both. That way the charges cancel out.
2 aluminum and 3 oxygen.
Yeah, so when you look at this, look at the lowest common multiple between the two. I have a 3 here, a 2 here. So if I get both of them to 6, I'll have the same number of charge, essentially. I'll have a plus 6 here, a negative 6 here. So I'm looking at the lowest common multiple. Here I want a plus 6, here I want a negative 6. To get there, I need 2 aluminum. That way, 3 plus 3, I'll get the plus 6. Here, I need 3 oxygens, because I'll have 2, 4, 6. I'll get a negative 6. So when I write the formula, it's going to be 2 and then O3. I have 2 aluminum for every 3 oxygen atoms here, when I'm talking about the formula. Because again, in the formula, there's no charge there. It's neutral. The charges cancel out. Now the textbook does show kind of like a shortcut way of this. If you look at your charges, you just swap them where they are. So the 3 plus, the 3 represents how many oxygens you have. The 2 represents how many aluminums you have. But the thing is, it's the understanding that the charges need to cancel out. Now here they have it like that, but the thing is, this is not in the reduced form. What number can you divide both of these by?
2.
2. So this is technically the correct answer. It's a 1-to-1 ratio between the 2. So they show this, but I'm not a fan of it, only because if you have the understanding, you don't need to kind of do the opposite. Just understand that how can I cancel out the charges? That's what you're trying to do. Cancel out charges. Now, this right here, oxygen 2 minus or magnesium 2 plus, there's only one guy. So this is called a monoatomic ion. Mono meaning one. I'm talking about an atom, just oxygen, and it happens to be an ion, so it has a charge to it. So monoatomic. Now you can have a situation where it's polyatomic. So poly meaning multiple, atoms are involved, and they happen to have a charge to it. So poly, more than 1. Normally, you'll see 2 or 3 involved. Yeah, 3 is probably the most you'll see. So these are polyatomic ions. You look at the first one. Notice you have 3 elements involved. Carbon, hydrogen, oxygen. So 3 elements involved. So poly. There's atoms involved, and it happens to have a charge, a -1 charge. Now these polyatomic ions behave as units. They're not any different than something like this. Here I have an oxygen ion, monatomic ion. Here I have the acetate ion, a polyatomic ion. Both behave the same in the sense, one unit. This just happens to be one guy. This happens to be 3 different elements involved. So you have 2, 3, that's 5, 6, 7 atoms involved here. It's just the unit is bigger. It has a net charge of -1. So it wants to gain 1 electron. So you keep it as a unit. It's just bigger. that's all it is. So polyatomic ions behave as a unit. They're exactly the same as something like O2 minus or Mg2 plus. They're exactly the same, it's just more than one element is involved. That's what you have to keep in mind. Now, the table that I gave you, this one here on the back side, has some of the most common polyatomic ions. So notice for, except the acetate one, everyone else has 2 elements involved with them. So it's always 2 elements involved. And again, they behave as a unit. So this whole thing has a 2 minus charge to it. Not just the oxygen, the whole entire thing. It behaves as a unit. Think of like families. They behave one collective family. You don't look at each individual one. Each individual one makes up the whole family. So these are polyatomic ions. You treat them the same way like you treat, let's say, the oxygen. So if I have a situation where here I have magnesium, and then here, this happens to be a polyatomic ion called nitrate. You treat it the same exact way. Here I have a 2 plus, here I have a negative 1. You need to cancel out charges. So how am I going to do that?
I know 3 in parentheses and then put a small 2.
Yeah, I need 2 nitrates for every 1 magnesium. Because notice now my charges, this side is plus 2, this side is negative 2. The charges will cancel out. The only thing that I have to do is indicate somehow that I have 2 units of this. The way you're going to do that is using parentheses. So I have magnesium, then I have 2 units of nitrate. So notice I put that in parentheses. You have to put it in parentheses, otherwise, if you write it like this, it looks like you have 32 oxygens. Right? So this is not right. You cannot do this. You need to put parentheses to indicate you have 2 units of the actual nitrate. And they exist like that. In solution, magnesium nitrate, so it acts very similar to salt. You have water, you can put magnesium nitrate into it, magnesium nitrate will dissolve. When anything dissolves, it breaks apart into its ions. So when it breaks apart, you have magnesium and nitrate. Nitrate stays together like that, doesn't separate. So it's the same thing as something like this, magnesium oxide. When this, you split it up, right? You have magnesium and oxygen. This is very similar to nitrate. It's negative, right? This happens to be negative 2, nitrate happens to be negative 1. But it's not any different. It still wants to gain a certain amount of electrons. Okay, so the ones that I've showed you so far are very basic, yes. Yeah, you have to make sure you write that down. Oh, you can write it down. Sorry. Now, all the metals that I've showed you so far are the ones that always form one type of charge. What do I mean by that? Let me show you here. These guys. So if you look at this, looking at only the metals, right? So these are the non-metals, I'm not gonna look at this. But these here and group 1 and group 2, these metals always like to form whatever the charge is indicated here. Now the way to remember this is, if you look at the group number, it tells you what charge it likes to be. So if you look at group 1, notice all of these have a positive 1 charge. Group 2, all have a positive 2 charge. And then group 3, all have a positive 3 charge. So the group number tells you the charge. Now it doesn't matter what compound I look at, you will always see that same charge. Example, you had magnesium oxide, you had magnesium nitrate. So it's magnesium in both compounds, but they're different. If I look at their charge, notice magnesium likes to form a +2. So it doesn't matter what compound I look at. Any compound that has magnesium will always have a +2 charge. Always wants to form that charge. If I look at aluminum, it doesn't matter what compound it's in. It will always form a +3 every single time. So they're very consistent in that sense. Yes?
So then the 2 that's after the parentheses, we distribute into the magnesium as well?
No, only what's within the parentheses.
Okay.
So it's the same thing like when you're doing math, right? You have something like this 2 only gets distributed within the parentheses. We're not going to apply it to the 6.
Okay.
Because that's outside the parentheses. Okay, so going back to this, when we look at a metal, and it only forms one type of ion. So that, we're talking about the group 1, group 2, and group 3. Only forms one type of ion. That's important to understand, because it's going to change how you name the compound. Now, you can have a situation where the metal likes to form more than one type. This happens with transition metals a lot. So transition metals, you'll see that. And those are the ones, if you look back to that table, it says transition metals will form cations, they want to lose electrons, but they're not very distinct. You look at copper, depending on the compound, likes to be +1 or +2. It just varies in the compound. It's not consistent. So these are the ones that are consistent. Notice they're in group 1, group 2, group 3. You do have 2 transition metals that behave like the main group elements. That's zinc and silver. These 2, and there's also cadmium. This likes to be a +2. So these 3 you have to know. You can't, there's no way around these 3. You have to know that they always form. Zinc always likes to be a +2, silver always +1, and then cadmium always +2. You can figure it out if you look at the periodic table. Use these numbers to help you. So this is 11. Use the 1 to help you. Silver is always +1. Use the 2 to help you that zinc is +2, cadmium is +2. So these, even though they're transition metals, they behave like group 1 and group 2 metals. They're always the same. They don't like to change. They don't like to deviate from how many electrons they like to lose. Now, these guys are the ones that like to form multiple charges. Now, you don't need to memorize this, how to figure it out. So if you look here, tin likes to form a +2 and a +4, and then if you look at copper, likes to be a +1 and a +2. So it's not consistent in their actual charges. They're very all over the place. Now, for us to keep track of the charges, the old system was a little bit annoying. This was very tedious to do. They would change the actual ending to OUS for the charge that was smaller and IC for the charge that was larger. But the thing is, it wasn't consistent in the sense that you have to memorize that tin always was a +2 and a +4, but copper was a +1 and a +2. So there was no consistencies in that sense. So this is the new system that's used. Now this system is very straightforward. You gotta know your Roman numerals, up to 10. The Roman numeral tells you the charge. So notice here you have tin 2, that means tin has a 2+ charge. When it's IV, that means 4, so here you have 4+. So you gotta know your Roman numerals. If you don't, then it's gonna throw you off up to 10. So here you have that. So you have 1 through 5 and then 6 through 10. When you're doing 4, the I comes first, then the V. When you're doing 6, the 5 comes first, then the I. So notice here 9, it's the I first, then the X. And then if you had 11, it would be X, and then the actual Roman numeral.
There's no reason for us to try to learn the whole system at all, right?
Not past 10. You
No,
don't
I
need
mean the old system, there's no
No,
reason for
no, because it's not used anymore. Like if you search anything, they'll always have the old system as other names. They'll always have it in there, but they're not gonna expect you to know that.
Alright.
So there's no point. Yes.
Do we have to have this memorized for our quiz next week?
Yeah, the quiz for sure. You'll see Roman numerals. So again, the Roman numeral tells you the charge, not how many you have, but the charge. We're gonna do practice with that, and you're gonna see that. The common thing I see is people automatically assume that's how many I have. Okay, so when we're naming, whenever you're naming, you name it in the order that's provided to you. So if I have something like this, right, you name the metal first, and you name it, you don't change anything about it. Na represents sodium. So I just write sodium. Now, the second element is chlorine from the periodic table. But what you do is you add IDE. You have the base name, you take off the actual ending, the suffix, and add IDE to it. So instead of chlorine, it's chloride. IDE. I have it right here.
Do you do that just on the non-metal or just second?
Just the non-metal.
Okay, so it'll be, I guess the second one will.
Yeah, the second one's always the non-metal. So you can see that here. You look, fluorine, this is the non-metal, right? When it's an ion, you keep the base name, chloral, and then add IDE. So it goes from chlorine to chloride, IDE. You have oxygen, when it's the ion, it's OX, so then you add the IDE, so it's oxide. You hear fluoride a lot, right? That's fluorine in a compound. So fluoride, iodide, sulfide, nitride, IDE every single time. So this is when it's an ion, it's in a If it's by itself, you would just say oxygen. You wouldn't add the IDE. Okay, again, if you have a metal that forms multiple charges, the naming is exactly the same. Notice these two are exactly the same. The only difference is you have to indicate the Roman numeral in parentheses. So this is the extra component that you have to add in every single time. So let's practice this part. Okay, look at number 3. Ionic. So potassium, does it always like to form one type of charge? Yes, it's in group 1, right? Always one type of charge. So you just name it how it is, potassium. And then the oxygen changes to oxide. So just potassium oxide. You don't in no way indicate that there's 2. That you can always figure out because potassium is always +1, oxygen is always -2. So coming together, you can always figure out the formula. You never indicate how many you have in the name. Now, looking at this, you have gold. Can you figure out its charge by looking at the periodic table? Does it fall in group 1, 2, or 3? No. So here I have to use Roman numerals to indicate the charge. The way you're going to figure out the charge is look at its counterpart, iodine. Iodine always wants to be a -1. It always likes to do that. So when you have 3 of these, but only 1 gold, gold has to hold a charge of +3 to cancel out with those 3 negative charges here. So when I write this name, I have to say gold, and then in parentheses, Roman numeral 3, and then the iodine changes to iodide.
How did you know that it folds a -1, like the iodine?
It's always, if you look at the non-metals, the last two rows, except this one, group 8, but these always are the same. They behave similar to the metals, but instead of losing electrons, they like to gain.
Okay.
So group 6 always wants to gain 2. Group 7 always wants to gain 1. So these behave like this, but instead of positive, it's going to be negative charges. So notice iodine always likes to be a -1. So here I write gold, 3 with the Roman numeral, and then iodine. Number 7. How would you do that one?
Sodium chloride.
Yeah, you just name the metal, right? But sodium is always +1, so I don't need to show a Roman numeral. And then fluorine turns into fluoride. Okay, you should be able to go in the opposite direction too. So far we just had the formula, you gave me the name. Now what if I give you the name and you give me the formula? So if you look at number 14,